All right, thank you for those of you who are joining. I apologize for yesterday's internet snafu. That doesn't often happen. It's actually has been, in my case, it's been the first instance in which I actually had problems with the internet. But in this case, we shouldn't have any problem. I just ask that those of you who are joining, if you just turn off your video and mute yourselves, and use the text option to basically chat, chat here for a question, chat for a question. Feel free to chat with me regarding that, but otherwise, we'll try to minimize the, the amount of bandwidth I use, because that could be an issue actually related to the fact that I'm using a lot of data, or some other internet throttling issue. It has never been an issue in the year and a half or 2 years that I've taught this section. And if you go to the YouTube channel, you'll see that I've uploaded about 70 different sections. So I'm not sure what the issue is here, but hopefully we won't have it today. So what are we going to do today? Well, if you look at the if we look at our familiar RStudio environment, you'll see I have 3 data frames loaded into our environment. 2, I actually loaded using this car data package. So this is basically a package that that we talked about yesterday that is available if you look at this help window and you go to the home page here, this little house is, and you go to CRAN task views, you can load a new page here. And CRAN task views, as I said before, is a great resource to find packages that you can then install and load. And then using this data function, you can actually learn about a particular package. So you can learn about the car data package that is affiliated with the car package, which is basically a rather notable one. And it's created by some economists for economists. And I showed the data function, how it can be used to actually load data using the data and then the name of the data set that's affiliated with a package, and then using the help function as well. You can learn about the data set. And as you can see, just as by proof of concept, it does take a while in R if you probably have a lot of data sets that you're loading, or if you have a lot of applications open, but you should be able to see right here that the Duncan package, using this function right here on line 6, you can actually load the data set into your environment. And there it is. It's a regular data set, and you can actually view it. So let's use the view function here. I'm going to clear my console using Option L, probably Control L if you use a Windows operating system. But we're going to look at this Duncan data set. And you'll see that it is actually a fairly simple data set. You'll see that it has 4 types of variables. But I also showed you this structure function. And the structure function is basically a more simple fundamental or base function that lets you get to know the data frame within the console. You can also, by the way, do this if you click the little arrow and open it for the data frame. You'll see you get the same kind of description. And both of them tell you a couple things. First of all, you'll see that the data frame itself has a factor variable or a categorical variable, and then it has some numeric variables. These are integer variables expressed as percentages. And if we use the help function on the data frame that we just loaded into our environment, we can know more about these these variables, these columns. And we'll see that these are actually numeric variables that are expressed as percentages. So these are, for instance, the one that we're going to focus on today, because this week we're talking about economics or econometrics, which is, if we're going to talk about what economists do, this is the kind of data set that's actually quite useful. It's not the only one that's available, but in part because this is actually, as I said before, this is actually a data set created by and developed by some sociologists. But it's a good example of where sociology and economics might actually meet, because you'll see that the variable that we're going to look at today is an income variable. And it's very much within the purview of what economists are interested in. Economics, just as a reference, is a social science discipline, and it describes the production, distribution, and consumption of goods and services. When we're talking about production, distribution, and consumption of goods and services, well, part of that is actually knowing what income is. And we're going to look at income in 1950. This is the percentage of occupational incumbents in the 1950 census who earned $35,000 or more per year. So this is a good example of how a variable that might seem categorical because it's a percentile or proportion is actually an integer. That is, it consists of whole numbers. Therefore, we can actually treat it as a numeric variable, and we can actually express it or understand it in terms of the average of something, because it's actually going to have, that's the way you're actually going to analyze the data. So we're going to use this variable income from the Duncan dataset to look at and illustrate the questions in the mission that have to do with the key concepts, key statistical concepts, where in your data set that we examined this week, we actually ask you to look at hours of work per week, and that's a numeric variable. We're actually going to just look at a different data sets and a different variable, just to show you that how this example can be illustrated using different concepts, different applications. But I hope to illustrate and help you understand the concepts relevant to the mission. So let's take a look at this. Basically, when we look at a data set and we want to know, we want to make an inference about it, the first thing we're going to do is basically, we're going to look at, especially when we look at tests of means, first of all, we have a random sample. If we have a random sample where we want to make an inference about something that is larger, that is generalizable to the population. And the way that we do that, let's just say as an economist, instead of looking at the number of hours employed people are working, we're going to look at what is the average income of people in the population given the information in our sample. And actually, you know what, I'm going to actually change this variable, because I actually want to look at, we'll look at education. That was kind of a funny, no, you know what, we'll stay with income. That's fine. They're both numeric variables, because an integer is the same as a numeric variable. The difference between an integer variable, which is indicated by the int, and a numeric variable, which is the num, is that an integer number is countable. So think of, just take your fingers out and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's an integer. A numeric variable might have decimal places in there. Now that doesn't make too much sense here, because age expressed in this employed ACS dataset, I believe, does not have any fractions or decimals in there. Still, it's one of those idiosyncratic aspects in which R will read in a number differently. The other thing about the difference between a numeric variable and an integer is always positive. It's a natural number. That's the way R will identify or read in variables. It really doesn't matter for practical applications. And I can show this to you because we're going to use our favstats function. If we remember this from our numeric dataset week, and we're going to take a look at this income variable, and we're going to use the data, and we're going to use the Duncan dataset. If you want to replicate the outputs from that first question in the mission, you can actually just replace income with the variable, which one is it? Hours week. And keep in mind, you're going to do capital H here. So you're going to do H and then lowercase hours, and then capital W and then lowercase k. And the data will be this employed ACS. And you can typically type tab if it requests an autocomplete. And I'll run that for just to show you. What did I do incorrectly here? That should work. Hold on for a second. Oh, I know what I did not do. I believe I did not load the Mosaic package here. Oh, I did. Let's take a look at that one more time. Let's just see if that is required as well. Well, let's try it with the Duncan dataset first. What am I doing? What's going on here? Hold on for a second. If I look at the example for favstats, Oh, hold on for a second. Does it require me to put this tilde here? Hold on for a second. That could be it. Yeah. So this is an example where, if you recall, the Mosaic is trying to standardize or really promote this idea that you have this little tilde operator here that is kind of a, you'll see it in the linear regression examples, but it's supposed to sort of express that everything to the right of your argument are the inputs to what it is that you printed the console. I ask that those of you joining just make sure you suppress your video, just to make sure that we don't have any internet interruptions. So what I wanted to show you is basically, let me clear the console so you can see this a little bit better. If you want to produce the output that we have for this week, you can actually see that the output is you can use it with the favorite stats function, and that's based on a random sample of the population. And we ask you some questions related to that output. I just want to show you how to do that. We're actually not going to use that. We're going to use some other output using a data set that we had found and that you could analyze. And I encourage you to explore the packages available and try this out on your own using the data function. So let's clear our console and look at these concepts using this other data set. So let me, pardon me, I'm just actually repeating the function rather than clearing the console. So this is option L or Alt L will clear the console. That's your keyboard shortcut. We're going to put our cursor next to this this output here, and we're basically going to take the mean, sorry, the descriptive statistics here, and I'm going to show you how to do a couple things here related to inference, statistical inference. So what do we have here? Well, what we have here is we have a mean income, and if we look at the help viewer, we're going to use the back arrow here, and we're going to go look at this Duncan's data set again, and we're going to understand what this mean income variable is. It is the percentage of occupational incumbents in the census who earn $35,000 or more per year. So we have an average percentage, which is 42. The standard deviation is 24. And we have a range from 7 to 81. So our estimate of the U.S. population, or the U.S. census, from this random sample, technically because it is a random sample, we could actually know what the population is, but this is actually a random sample of Americans in this particular study. You'll see that this is quite a small data set, right? It only has 45 observations. It's a very small data set. So our inferential statistics are going to be rather imprecise, you could guess, because 45 individuals, we're not even sure if this is actually going to be that representative, and we'll see whether or not it is. It's a very influential study because it has a lot of data, but of course, when you have a lot of information, sometimes you have to have a smaller sample size. But let's take a look at this. So here we have a percentage variable that is expressed as a numeric variable because it is something that is varies as an integer in the sample. And we can look at that using the view function. We'll see it's a numeric variable. So look at this income. You have someone, for example, who is a coal miner. And then you'll have, sorry, this is, I think what it is, it's, hold on, if you look at the data set, yeah, it's the type of occupation that they have. So you have people in the sample are either professional and managerial, white collar, or blue collar. And you'll look at the person with the lowest income was a coal miner. This is a blue collar worker who has a variable 7. And this is the percentage of occupational incumbents who earn $35,000 or more. So basically, the percentage of people within this occupation who earned more than 36,000 US dollars. And you'll see that not very many coal miners earned above what was probably then about the median income for men. But you'll see that if you look at the highest one, if you look at the highest income value here, someone has a question. Yeah, go ahead and ask the question. Someone has a question? Feel free to ask a question if you do. But the point here is the highest value is someone who's an engineer or a dentist. They belong to incomes, occupations where the income is higher than 35 grand, which was, I guess, quite a bit in 1950. Reporters were also paid quite a bit. A conductor is an interesting sample here. I think this might be a train conductor, not a musical conductor. It's the highest working class position. An engineer, a railroad engineer at the time in 1950, was the highest earning occupant. So these are occupational characteristics, even though we have individuals. There are enough individual differences because each person has a different occupation. So what this data is actually, it's a variable. It describes the sample, and we can actually make an inference here. We have we have a variable that tells us the average in the sample, which is basically the average in the people who earn, the average number of people in the sample who earn more than 35 grand per year. Okay, that's about, so 42% of this sample earns more than $35,000 a year, or sorry, 3,500 per year. And 7%, and that's an estimate that ranges from 7 to 64 within individuals. What we want to do now is, given that this is the average in the sample, we want to know in the population, if we can generalize this to the population, what is our estimate of occupational incumbents who earn more than this much per year? What is this average, this X bar? What does this reflect in the population? And this is where we're going to do hypothesis testing. And this is relevant to the key statistical concepts that we review. So if we're an economist and we want to make an inference, we first want to know, what is the point estimate for the population mean? I think you might be having some difficulty hearing me, so I'm going to let me know if you do. But the question we have here is, what is the point estimate in the population? Well, the point estimate we're going to have is this sample mean. So remember, sample mean, we find, is our point estimate. It simply means it is one value that is our best guess. The point estimate is our best guess at the true population parameter. Okay. Now, what is the sample standard deviation? Well, the point estimate, as I said, is the sample mean. So here it would be about 41.87, rounded to 2 decimal places. And this is the point estimate for the population mean for the percentage of above 35K. And the sample standard deviation for this mean, or this point estimate, is approximately 24.44. It's the standard deviation. And we can see that there are 45 people within this sample. So using what we know from about sample statistics, how would we construct a 95% confidence interval for this point estimate? And what does this tell us about our sample regarding the population? Now keep in mind from lectures we talked about the 95% confidence interval also is known as a z-interval, and we use this, we infer the sample mean to the population using the standard normal distribution model for the sampling distribution. So what do we obtain and how do we interpret this interval? And we use the sample standard deviation as an estimate for the population standard deviation. And we do this because we know that 95% of randomly drawn z-scores from the standard normal distribution lie within about plus or minus 1.96 within the interval of the center of the normal distribution. So what we find then is that to create our 95% confidence interval, we take our point estimate, our sample mean, and we add and subtract approximately 2 times our standard error, or 1.96 times our standard error. So the question is, how do we first find the standard error? And this is going to be our estimate of how much our variation in our sample is, sorry, how much variation we would expect in our point estimates. It's a range of possible values within the population of our point estimate, and we can find our standard error is equal to S, or our sample standard deviation, divided by the square root of n, or the sample size. So our equation for standard error is going to be S divided by the square roots, and I'm writing this out using R functions, the square root of our sample size, n. And here we use, and then here note that in applications we use the sample standard deviation S in place of the unknown population standard deviation sigma. So given that we know that S is equal to 24.44, and given that we know that our n is equal to 45, then we know that our standard error is going to could be evaluated using S divided by the square roots of n. And if we print this out, and we're going to round this value out to 2 decimal places, I'm going to show you through R what the standard error will be for our population estimate of this income variable in the Duncan dataset. That's our standard error here. And basically I just found it by writing the equation for standard error, and then of course rounding it to 2 decimal places, and using the sample standard deviation and the sample size to estimate the standard error. Now the standard error by itself is a measure of the variability of the estimates in the standard normal distribution, but it does not tell us, it is only part of the way in which we construct the 95% confidence interval, because the standard error is only one part of understanding the 95% confidence interval. Remember that based on the sampling distribution and the standard normal distribution, we know that 95% of z-scores will lie between -2 or +2 about, technically minus -1.96 and positive 1.96 of the center of the distribution. So that means we can construct a 95% z-interval if we take our point estimate plus or minus 1.96 times the standard error. So the 95% confidence interval then is constructed by this: 95% CI is constructed is equal to the point estimate, we'll just call it PE, plus or minus the standard error times 1.96. So if we do this, then we can actually get the lower bound. So then the lower bound point of the confidence interval would be, so what's our point estimate here? Our point estimate here is equal to that sample standard mean. So it would be the rounded value of our mean. Remember, we talked about this earlier. And then we would round that to 2 decimal places. So this is what our point estimate would be. So let's do that. And we can see that that's printed out right here. Actually, if we print it in the console, well, you'll see it's 41.87. So then that would mean that our lower CI value would be equal to our point estimate minus 1.96 times the standard error. And I'm putting this in parentheses, sorry. You shouldn't have to, but I'm putting this other function in parentheses just to clarify the fact that we basically can construct our 95% confidence interval with these 2 estimates. These are going to be the lower and upper bound values of our 95% confidence interval. And I'll put 95 here just to clarify this is actually one of many confidence intervals that we could. Hello, I think I might have lost you for a second. Can you guys hear me? Can you guys hear me? Hello. Yeah, sorry about that. Shoot. Well, somehow I got locked out for a second. I don't know what the issue is. Honestly, I tried my best. I apologize. In any case, there was a brief interruption. It actually means that we'll have to have this recording in 2 sections. I'll try to patch together the 2 video recordings, but I don't think we lost too much time here. I just wanted to show, I was in the middle of typing and that's showing you that we can actually estimate the lower bound and upper bound of the 95% confidence interval separately. And this is basically what we're doing here is we're showing based on statistical inference that if we take the standard error and we multiply it by a value of plus or minus 1.96, that is how we construct the 95% confidence interval. And if we run this, well, because I'm starting all over again, I realize my environment actually does not include the data set that we used for analysis. Shoot, so let's try to get this back in. Well, hold on for a second, this is strange. Yeah, it no longer exists. So we will try to get our data frame back in to our environment. Okay, so I got to rerun the mosaic function. Let's require all of these right here. All right, and we're going to get the data frame in, and it'll take a little while. And if worst comes to worst, we'll use some other data frame. Let's see what happens, though. Yeah, okay, so it didn't take that long to actually get our data into our environment. Good. So we use that favorite stats function, and then we're basically going to estimate we're going to find our point estimates. And that was actually the very first thing we've done. So let me put that here. And we round that to 2 decimal places. And there's our point estimate. So that's our best guess of what it is the income variable in the Duncan data set would be in the population. But of course, that's estimated using the standard error, which is a measure of variation. On average, how much does our point estimate vary in the sampling distribution? On average, our sampling our point estimate would vary in the sampling distribution by about 3.64. So there's some variability in terms of, on average, in our sampling distribution, it would vary somewhat, the percentage on average. And if we round the the standard error by 2, that's actually going to be the value that we want. So let's replace that with our rounded value. So here we have the sample standard error, and here we have the sample standard deviation, and then we have the sample size, and we have our point estimate. So to distinguish these, remember that SE, the standard error, is on average how much would our point estimates, 41.86, vary in the sampling distribution if we follow the standard normal distribution. And this, given this measure of the average of the sampling distribution, so the average standard error of our point estimates, we can then construct confidence intervals of various sorts. The most common one is the 95% confidence interval, in which we take our point estimates and we subtract plus or minus 1.96. And if we do those, we're actually going to get a 95% confidence interval that is basically, do we have those values? Yeah, we have those right here. If we print those, we're going to print, we're basically going to have a value that is, varies between, so our 95% confidence interval for income in the Duncan dataset would be 34.74 and 49.00. We'll often do a comma if we're going to express the 95% confidence interval. So what that means then is that given our estimate, our point estimate of 40, or was that point estimate? 41.87, that means that our 95% confidence interval is going to vary considerably from that point estimate in our sample. And what that means then is that we are 95% confident that the true population mean of income in the is in the interval between 34.74 and 49.00. So we're 95% confident that the true population mean lies between these two values, these two upper and lower bounds of the 95% confidence interval. Now, from this, we can actually construct other kinds of confidence intervals. What if we wanted to construct an 80% confidence interval, or a Z interval, using the standard normal distribution? How do we obtain this? Well, we simply take our standard error and our point estimates, and we multiply these by plus or minus 1.28, and we take a smaller value because this is based on the probability distribution of the standard of the expected number of point estimates or values within the standard normal distribution. So what we're doing here is we're actually taking an estimate that is going to be more precise, but it's also going to lower our confidence to 80% that the true population mean will lie within this interval. So we're going to have a more narrow interval, but our confidence is going to be lower. So when we construct the lower, when we construct the confidence interval here, we're going to print these out, print lower 80 CI, and then we're going to print the upper 80 CI. What I'm doing here then is what we're going to do with an 80% confidence interval is make a statement about our mean that will be more precise because it's going to have a smaller range, but it's going to lower our confidence that the true population mean really lies within this interval. So there's a trade-off here. So what we have here is we have an 80% confidence interval for our mean, which says that we are 80% confident that the true population mean will lie within 37 and 46, or 37.21 and 46.53. That means that in 20% of samples identical to this one, the true population mean would lie outside of this interval. So our claims about the true population mean are more precise because the range is smaller. If we can compare that right here, because if we just print the in the console these values for the 95% confidence interval, let's just do that. We'll see that the range is actually a little bit wider. Hello again. Sorry, this is frustrating. You should be able to see the shared screen again. I got kicked off again. I'm not exactly sure why that is, but I'll talk to IT about that. Again, you should be able to see me now. I'm pretty confident this won't happen again. Let's just try to get through this, and I hope it won't happen again. Unfortunately, we're going to have to run the script again. That's okay, though, because here's the advantage of actually writing your code out, I have to say, which is that basically you're able to replicate your analyses. So if you do lose track of where you are, this is the advantage of using the script rather than just typing within the console. As you can see, I just printed out here the 95 upper bounds of the 95% confidence interval, and then the 80% confidence interval for our income variable. And as I pointed out, the difference between 49 and 34 is wider or greater than the difference between 46 and 37. So the 95% confidence interval tells us that we are 95% confident that the true population mean for income in the Duncan data set lies within 34.73 and 49.00. Now, we are 80% confident that the true population mean lies between 37.21 and 46.53. So the difference between an 80% confidence interval and a 95% confidence interval is that you get greater precision in our possible range of values for the estimated mean. But we typically will not use an 80% confidence interval because we're actually increasing the probability that our estimate does not include the true population mean. So I basically have shown so far how to construct the standard error using sample, using a sample available to us, how to construct an 80% confidence interval, and how to construct a 95% confidence interval, and then how to interpret those. Now we can also do a 50% confidence interval, something that you would never see in the real world, mainly because a 50% confidence interval tells us that we're only 50% confident that the true population mean would lie within this interval. And we would do this by taking hold on for a second, let me make sure I have this written out correctly. By taking our standard error, our point estimate, and subtracting plus or minus only 0.67 times our standard error. And it's always going to be 0.67 times our standard error because this is based on the properties of the standard normal distribution, which is based on the idea that our sampling variability, if we take random samples and repeat those random samples, then they're going to lie in the standard normal distribution. They're going to be bell-shaped, bell-curved. And if we want to plot this, we can do the plot distribution function. Just to show you what this is, if you recall, I believe you can just do this. I think that's a capital D. Just as a reminder. Hold on. Oh, shoot, there's a typo there. Hold on for a second. Sorry. Why am I, maybe it's the, sorry, it's the pdist function. Ah, that's what it is. Sorry, some of these function names have changed over time. Well, I could show you some ready-made code here, but why am I not finding this? Hold on for a second. Well, that's irritating to me. Okay. This is how you'd find it within Mosaic. No. Oh, okay. Hold on for a second. pdist. See, the base function you could use here is the distribution function, actually. Oh, it doesn't really matter, except if you just look at the, yeah. No. Okay, I feel like I'm getting us into a distraction here that's not worth pursuing. The point I want to make is you can construct the 50% confidence interval. And if you do that, you'll see that you get an estimate that is going to be more precise, but it's going to be actually characterized by wait, we cannot get the lower confidence. Hold on, well, let's see why that did not work. Oh, there was an. Make sure that you have the operator symbol here. That was the problem that I've had here. So if I run that, and then we print these two values, you'll see what's going on here. Lower and upper. Hold on for a second. There we go. We see that our lower and upper 50% confidence intervals range from 39 to 44. That's much smaller than our 80% confidence intervals, which is between 37 and 46, and then our 95% confidence interval. So as our confidence interval becomes more precise, that is, as the range between the upper and lower bounds of our confidence interval shrink, our confidence also shrinks as well. So typically, we will not use an 80% confidence interval, and we definitely would not use a 50% confidence interval, because those would tell us that our true population estimate of the mean would lie between, that we're only 50% confident or 80% confident that our point estimate lies, the point estimates we're only 50% confident and 80% confident that our interval contains the true population parameter. That's why we would use a 95% confidence interval, because as a rule of thumb, it's considered to be the most, probably the least, but I guess you could say that the least likely, or to have of an extremely wide range, yet still diminishes the possibility that we have a range that does not exclude the true population mean. It's only in 5% of samples would we actually have a true population mean that lies outside of our confidence interval. So what we can say then is, based on a sample of 45 people, we're going to have a confidence interval that ranges from 34 to 49, and we're 95% confident that our true population mean of 42 lies between 34 and 49. So what that tells us then is, when we think about a point estimate is just one value along a range of plausible estimates. And when we talk about inferential statistics, we're moving from something that describes or condenses information such as an average or a measure of central tendency, to one that describes a range of plausible estimates. And this is what a 95% confidence interval is. So our point estimate is only the center of a range of plausible estimates of our true population mean. Now, if we want to talk about a hypothesis testing, we're running a little bit out of time, but that's the second part of the conceptual section. And here I just want to talk about the fact that when we talk about hypothesis testing, we're still going to actually use the standard error here to run a t-test. So in this case, if we're going to talk about hypothesis testing, just keep in mind that you can use the standard error for hypothesis testing as well. This is why the standard error is so useful. It's not only used in terms of inference, but it's also used to construct an estimate of for a t-test. Because both tell us about the range of plausible estimates given our sample. So I think that's about it for this this section. Unfortunately, I apologize for the interruptions, but if there are any questions about the range of possible estimates and about how we construct a sample standard error and use that to construct a confidence interval, please let me know. Do you have any questions about that? Otherwise, I would encourage you to look at the playlist that we have available online, where we run over, where we review the second part of the problem set. I review the code, and then after the problem set is due, I actually also review the concepts. And if you have any questions, feel free to post to the discussion board as well. Thank you so much, and I apologize for the interruptions. We'll make sure to post those as one complete video, so that way it'll be seamless. I apologize for the technical problems, but in any case, good luck with the mission. Feel free to ask me any questions, and I hope this has been helpful for you. Thanks a lot.